Okay, this is the solutions to the Gram-Schmidt problems. For the first part of this, I'm just going to work straight from MATLAB because that is my expectation of how you would do this. In the first problem, you have two vectors, 3, 4, and 1, 0. So we're going to enter that. Hopefully you have the MATLAB code for Gram-Schmidt entered into your computer. If you're having trouble getting that in there, either send me an email or do one of the drop-ins and we'll see if we can't walk through that. But the M file is how you should be doing these problems. Alright, so that said, the first one you have a vector 3, 4, and you have vector 1, 0, and we Gram-Schmidt that vector. And it gives me back, and now you read the corresponding vectors in the rows. So this would be 0.68, or say 0.6 and 0.8, and 0.8 and negative 0.6. In the second problem, you're in R3. You have 1, 0, 0. You have 1, 1, 1. And you have 1, 1, negative 1. Alright, so that comes back when we do Gram-Schmidt as 1, 0, 0, 0, that's I think root 2 over 2, root 2 over 2, and then root 2 over 2 and negative root 2 over 2, I believe. Let me make sure that I have that right. Yeah, that's root 2 over 2 in that problem. So you can leave it as decimals. That's how I left it in the answer sheet. It's all good. You're fine. The third set of vectors you have here are 0, 1, 1, 1, 1, 0, 1, 0, 1. So if I perform Gram-Schmidt on that, you get 0, 0.7071, 0.7071. You get 0.8165, 0.4082, and then negative 0.4082, and then 5774. Negative 0.5774 and 0.5774. So like the next one is one that you definitely don't want to do by hand because this is like an R4. So this is 3, 4, 0, 0, negative 1, 1, 0, 0, 2, 1, 0, negative 1, 0, 1, 1, 0. And then we perform Gram-Schmidt on that. And there we go. So we're going to get 0.6, 0.8, 2 zeros, negative 0.8, 0.6, 2 zeros, 3 zeros and a 1, 2 zeros, a 1, and a 0. Okay, so the we'll take a look at numbers 5 and 6 a little bit by hand here, and then we'll take a look at 7, which is the proof. Problem number 5, we're now working in P3. So the first thing we want to check is this an orthonormal basis? And you can check the first two vectors. Take the inner product of x squared and x squared plus 2x. We'll use the standard inner product here. There's nothing in the constant terms for either. It's 0 and 2 for the linear term, and 1 and 1 for the quadratic term, which just gives me a norm of 1, which is not 0. So I'm not orthogonal. So this is not an orthonormal basis. What you do is you say, okay, I have 3 vectors here, and I just take the coefficients. So x squared becomes 0, 0, 1. X squared plus 2x is going to be 0, 2, 1. And then 1 plus 2x plus x squared is going to be 1, 2, 1. Okay, feed this into Gram-Schmidt. That's going to turn out 0, 0, 1, 0, 1, 0, 1, 0, 0, which ironically is the standard basis. It's x squared x and 1, which is an orthonormal basis for P3. So feeding that thing into Gram-Schmidt turns out to be just the standard basis. All right, so let's look at number 6. All right, problem number 6 is the same as 5. We first check orthogonality. So the one vector is 3x squared over 5 plus 4x over 5. The other one is, the second one is negative 4x squared over 5 plus 3x over 5, which, when I do the dot product of the coefficients here, I'm getting negative 12 over 25 plus 12 over 25, and there's no constant term, so that's 0 is going to give me 0. If I check the first vector against the third vector, I'm getting 0 for the quadratics term, 0 for the x term, the linear term, and 0 for the constant term, so that's going to give me 0. And if I take the second one times the third one, I'm getting 0 for the quadratic, 0 for the linear, and 0 for the constant, all 0. All right, so this tells me that I'm orthogonal. Now we want to look at, is it orthonormal? So we take the magnitude of each of the vectors. So 3x squared plus 4x, both over 5, right? So this is going to give me square root of 9 25ths plus 16 25ths plus 0 is 25 over 25, which is 1. That's good. Negative 4x squared over 5 plus 3x over 5, again, becomes 12 over 25, sorry, 16 over 25 plus 9 over 25 plus 0, which is 25 over 25, which is 1. And then the last one is just the magnitude of 1, which is going to be 0, 0, 1, which is square root of 1, which is 1, which means that this is orthonormal. And in fact, because it's right-sized, it has a magnitude of 3, it is in fact orthonormal basis for P2. Right, so this is an orthonormal basis for P2. All right, 7 is probably the trickiest part of the page, and we'll take a look at why that works. Okay, before you attempt this proof for number 7, you should review the idea of Fourier coefficients that are in the notes, because we get leveraged here. We're saying that we have some set of vectors, u1, u2, out to un, that form an orthonormal basis for Rn. Alright, so we know that V is a vector in Rn, right? That means that you can take a linear combination of the u's and get V. Okay, now we've shown that what you can do, and this is those Fourier coefficients, is that if this is an orthonormal basis, then you can write each of these C's as the dot product of V times U1 plus V times U2 times U2 plus V times U3 times, let's make it UN times UN, right? So a little bit of algebraing here. So if I'm going to let the left be V times V, then basically I encapsulate the right in a bigger inner product, right? Okay, so manipulating a little bit here. This is a constant, right? So I can pull that out of the inner product. Do the same here. Do the same here. Now, inner product is commutative, so I can just rewrite these as being v u1 squared plus v u2 squared plus v un squared, and just define the inner product like xy be the dot product, and we end up with, well, let's see, the inner product of v with itself becomes the magnitude of v squared, and then these all become the dot products, so that's u dot v1, or sorry, v dot u1 squared plus v dot u2 squared plus v dot un squared, which is what we're trying to prove. And there's your proof for number 7. So if it's a little confusing, take a minute, go back through it. That's why videos sometimes help. And if it's still troubling, let's talk about it during a drop-in, or send me an email, or we'll work it out somehow. All right, thank you.